Okay, good afternoon, everybody. We're going to start in a minute or two, just to give people time to log in. Especially if people are like me and couldn't find the right button to press. Okay. Good afternoon, everybody. Welcome to the third Industry Club meeting. These are really quite exciting times, and like most weeks, we've got a good focus on hydrogen and batteries. So I'm very pleased to have John and Emmanuel to speak to us today. We're starting with John Lowe, who is one of our PhD students from chemistry in St Andrews and moved to Keamig, who originally located just next to the chemistry building and then I've been in Dundee ever since. And John is going to talk to us about working with Platinum Group and Noble Metals. So John, shall I let you take over?
Yep, that's fine. That's perfect. Okay, let me share this presentation, hopefully. Okay, hopefully everybody can see that fine. Okay, so I'm going to talk about manufacturing with Platinum Group and Noble Metals. We as a company, Keamig, are part of Ames Goldsmith. Ames Goldsmith being the parent company based in America, and our parent company is primarily involved with silver and silver handling. And one of the interesting facts that I find from that is a quarter of all the industrial silver will go through Ames Goldsmith at some point during a year that's used industrially.
John, sorry to interrupt, we can't see your slides.
Oh, sorry. Okay. Okay. Is that better now?
That's good.
Perfect. Okay, so I haven't missed anything. Still the first slide. So as I say, we are Keamig is a company which manufactures precious metal powders, the alloys and pastes. Pretty much everything Keamig is everything other than silver, and we are the first step in green hydrogen from a PEM electrolysis point of view. We're also, if you think about it, we also are the first step in fuel cell as well, if it's PEM technology. So this is a picture of Ames Goldsmith. This is our factory. It is based in Dundee, and we have 9,000 square feet. Comprised within this building, we have 13 fume hoods, and we are ongoing in terms of ramping up what we have here as a capability. So we've actually invested, are currently investing $500,000 in electrochemical testing equipment to give us that catalytic feedback of the manufacture that we also do here. We also are investing in analytical equipment as well, and we have an ongoing production scale up. So what I want to actually talk about is current manufacturing considerations that we have here at CAMIG. The first question or first point that people say to me is if we're working with platinum or iridium or osmium or so on, that's going to be expensive. There's a cost involved with that, obviously. Everybody intuitively knows that the price of gold is really high, and if you want to work with it, yeah, it's going to cost you a lot of money to do that. And just a graphic on the right here gives you some sort of indication as to fluctuation. You can see that 3 months ago, the price of iridium was sitting at $2,500 US per troy ounce. We're now currently sitting at $6,000 per troy ounce. So yeah, over the course of 3 months, effectively the cost has, well, getting close on doubling, even tripling. Platinum, by that same token, has stayed fairly stable, but still expensive to handle. So to give you an idea of cost, this is a typical batch that we have towards the end of the production cycle. You can see here that we have close on maybe about 1 kilogram of precious metal, and if it's, you know, going by the iridium price, the spatula that you see here, that being roughly about 1 gram, would cost you £140 just in precious metal cost alone. So you can see that we don't encourage people to sneeze here. To put our process into a really super simplified idea for people, because I appreciate that not everybody joining in will be from a chemistry background or even the manufacturing background. I'm just going to simplify this and stay away from some of the heavier chemistry. But to keep it simplified, as I say, we have the idea is we actually start with bullion metal. In this case, I've just shown a picture of some of the silver ingots that we use in our sister plant, and that would be dissolved down and become a metal salt. So we would then take that metal salt, and this is really where sort of CAMIG kicks in from the metal salt side, and we would actually convert that ironically back to metal. But as you can see, we actually go for a powder metal, so we actually go from a full-on ingot to an actual powder, and that's what will then go to the next step of process, which I'll come on to in later slides. So first of all, one of our issues in our current manufacturing is we have to start with a salt, the metal salt, and as I say here, you know, spot the difference. There isn't really much difference to see here. It's maybe a bit chunkier on the right, but this is actually a salt from 2 different suppliers. It's actually absolutely the same specification, and if we actually run that through our process, it would actually give us different outcomes in terms of our quality. So this is one of the difficulties that we have, and I guess every chemical manufacturer faces the same problem. But when we think of this in terms of our cost, yeah, this can have a massive impact. The synthesis route as well is something that is very important to us. Which way do we go in the synthesis? For example, and gold is a classic example for us. If we take certain synthesis routes, we will end up with gold flake. Very easy to make gold flake, very difficult to make gold fine powder. And one of the secrets to the synthesis route is not just the starting salt, but it's actually what we put in there as a surfactant. And again, that will translate into a final product with a customer. And I've actually posed the question here, when is contamination not contamination? Well, it's when the customer doesn't mind it being there. So for example, the surfactant here in this case would be an organic surfactant, and in their process they would actually bake that out if they were going to actually coat that down onto a sensor, for example. So from that point of view, it's not contamination. Now, one of the biggest issues that I have within this building is that of recovery. So when we manufacture in batch, we need high recovery. So if I was an organic chemist, for example, and I had a recovery of 70%, I would be breaking open the champagne, going, that's a fantastic result. If I had a 70% recovery here, then yeah, I have a serious problem given the cost. So recovery then leads me to another issue, which is one of particle size. So if I make nanoparticles, it's easy to make nanoparticles. Can I recover them? Can I recover them efficiently? Can I get a 99% yield? So I actually have, I've showed two particle size distribution charts here. So the one on the left was actually the gold you've seen earlier. And that gold is sitting about 0.4 microns. And that makes that really nice fine powder. And in the next slide, I'll give you an example of why that's nice and important. But the one on the right here is equally as important, even though it's sitting up at the 20 micron size. This is actually an agglomeration of crystallites. And that again is important because it means I can recover it. So I can actually make nanoparticles so long as they all coalesce into a bigger agglomeration, which is then able to be worked further on. So this is just, hopefully you'll see this will come through. This is a quick video of in process. And you can see that as we process this, it will actually agitate itself within the solvent. In this case, the solvent here is an acidic aqueous environment. And the very fact that that actually falls back down and doesn't actually go into solution is very important because that helps us with our recovery. The picture you see on the right here, you can get an example of what I mean if it goes into colloidal solution. If I wash that through and I want to get rid of my contamination in my material, if I wash with this sort of colloidal problem, within 4 or 5 washes, this metal that you see at the bottom, well, it pretty much will be gone. And that's just not acceptable for us. So that's something I have to consider as we go through manufacture. So the cleaning and the recovery all impacts yield, which all impacts cost. Okay, so why do we make the powders? Well, one of the reasons for making the powder is to then take it into an ink or a paste formulation. And again, one of the problems that we have with the ink formulation or the paste is we need it to go into a stable solution. So you can see on the left here that this is just not miscible. These are a range of platinum powders, supported platinum powders actually on carbon. And so we have a range of felicities in this, hydrophelicities. And you can see that some are better than others. So do we change the solvent to suit the powder, or does the powder change to suit the solvent? That's one of the questions that we have to always consider when we manufacture. So you can see that the fourth jar here is actually a really nice stable composition, and that's all good if you're going to take that on and actually do some coating with it. However, if we're actually doing some washing and we actually want to recover that material, you could see that I would have some issues. So there's a quick video here. So this here is actually the gold that you've seen earlier, and can we get that to redisperse? That's one of the challenges. And as you can see, as soon as we give it a shake, it all very quickly goes back into a colloidal suspension. So that's very useful for us. Okay, so the fact that that will actually, once I actually leave that, when it's in colloidal suspension, it will actually fall back into a clear liquid with a nice fallout. And again, that's very important for recovery if that was at the wash stage. It's not so good if we're here and we're actually at the coating stage. We want that stable suspension to remain. So we're actually battling two different processes here. Okay, so this is the initial process flow, but with a bit more detail to it. So what I was initially saying with the starting salt, we can actually tell if that starting salt has actually came from all the way back from the metal ore, whether it actually came from a virgin source or whether it's actually came from a refined source. So why is that important to us? Well, for example, if my salt was an iridium salt, my virgin source would actually have high contamination of platinum in there. Now, 9 times out of 10, that is not an issue. Platinum's a useful, will have a useful synergy with the iridium anyway at that level. But if it was a refined material, we've maybe got some slightly different issues here. For example, it might be a spent catalyst that is being refined, and as it goes back through the process, there might be, as an example, high sulfur in there. So yeah, we have to be careful about the quality of it. Even though it has an identical specification, we know that the final product can actually be influenced even at this early stage. So our synthesis route will go through, and as I sort of alluded to earlier, if it's a known production, we will have a large scale and we will have a yield that we can work with, which is all dependent on the percentage of conversion of the salt, purification and handling and bottling. So each one of these stages impacts yield, which then will actually impact our loss. But if we were actually doing an unknown, an R&D scale, for example, the gold, and we're actually working at 1 gram, then that as a scale will have a big impact potentially on yield. For example, do we recover that full 1 gram? Is it, do we recover 0.8 of a gram, so a 20% loss? Is that just because of the scale, or if we actually tried to make 100 grams, would we suddenly lose 20 grams? So we're always considering, can we actually change things, and how easily can we change that, all under the auspices of cost. So cost is everything on this. And even when we get to the end stages, when we actually make the powder and we make the paste, at any stage this could fail. Even when it goes out for customer and the customer looks at it, it could fail at that stage. And a batch fail for us is obviously huge. Although we can recover it as metal, there is an obvious impact there. There will be natural losses through that whole process. So just to move on very quickly onto future manufacturing considerations. It's all well and good being here now with what we make, but what about going into the future? One of the common questions that I get asked is, is there enough PGMs in the world to make MEAs for PEM electrolyzers, as an example? Another question is, everybody says, will there be enough, is green hydrogen going to be the way to go? So the concerns from my point of view is more around the precious metal. So, for example, iridium and platinum, these have been the choice of material for electrolyzers. Over the last, certainly going back maybe 10 years and coming forwards to where we are now, iridium and platinum have shown to be the metal of choice. But in order to reduce platinum usage, and I'm talking about PEM as a whole, not just electrolyzer, I'm talking about fuel cell. One of the strategies was to use carbon as a support for the platinum. And by doing that, you can actually reduce your platinum usage down towards something like 30%, or as an average, maybe 20 or 40% platinum on carbon, and still have that same activity. Unfortunately, with the iridium, the problem that we face is that strategy of carbon is not a good one, because carbon will not survive that environment. So one of the strategies ongoing just now is that we actually make the iridium with a ruthenium alloy. Unfortunately, the ruthenium is the minimum metal, so therefore the savings are also minimal. But the way that we overcome this and actually maximise is to make the iridium go a long way. And one way to do that is actually have a very high surface area of this material. So as you can see, the surface area of the material here from this TEM image, you can see that our structures are very rod-like, and the surface area, for those in the know, is up at 140 meters squared per gram, which for a metal is really, really high. And so that's one of the ways that the iridium is maximised. But going forward and looking forward, I don't think that's enough. We live in a constantly improving our technological advancement, and so it's going to constantly change. It might be that in five years' time there might be no PGMs required for this. I doubt it, but even if that was the case, if you started now, there would actually have to be a time frame for that to go from nothing all the way to something that's actually developed and mature. So as we stand just now, PGMs are certainly here for the foreseeable. To give you an idea of where we're going with this, typically 8,000 kilograms per year is mined as iridium. It's a byproduct of platinum, so its availability is effectively it's a tenth of what you would get in terms of platinum. Is that enough when there's competing demands for iridium? So one of the very first slide I showed was the price of the iridium going high. This is probably influenced by the fact that this 2019 accord for the ballast, ship water ballast being treated has had a big impact on that. So yeah, there's competing demands for iridium. However, CAMIG has, over the last year and is going forward, is looking to actually support this iridium onto various materials, which will actually survive that environment. And so far, we've actually had a very hopeful material, which is advanced development, which is actually using 0.1 gram per kilowatt, as opposed to 1 gram, which is where we are currently. So that's a 90% reduction in iridium use, and if you multiply that through, then we should actually be quite good with the availability of iridium. So yeah, I'll skip over that, and given that's 20 odd minutes, I will cut here and just like to thank the University of St Andrews for hosting the event, and thank the Hydrogen Accelerator team as well for the opportunity to present. So thank you.
Thank you, John. That's fascinating. Nice to learn a little more about iridium. We'll come back to questions after the next presentation. We'll do them together. I see Kim has already started asking questions on live questions and answers. So please upload some questions and answer some questions now for John, so as we can come straight back in after Emmanuel has spoken. So thank you very much. That was really nice chemistry. Clear. So our next speaker is from Amity Power, who are based in Thurso and Oxford, I guess. So Emmanuel Weka is the lead technologist, and he's going to speak on profile, target markets, cell development approach, and product pipeline. So Emmanuel, hopefully the technology works. Over to you.
Okay, thanks a lot for that introduction, John, and thank you all for joining. I'm just going to try to share my presentation. Let's make sure you. Can you see that?
We can,
Yep.
thanks.
Okay, right. So yeah, today I'm not going to go into any technical details per se. I'm just going to give you an overview, a very quick overview of what we do at AMTI and our approach. And
you might like to just go to hide presenter view on the 3 dots. Just below the main slide.
Okay. Let's see that.
That's you.
So just hide. Okay. Right. Is that better?
And then go to full screen, I guess. Yeah.
Yeah.
That should. Yeah, I don't know why it's doing that.
Full screen.
That's better anyway. That's fine.
Is that better? Yeah, I don't know why it's doing that.
Okay.
Okay.
That's great. Now you can see the slides. That's the important thing.
Yeah. Okay. All right. Thanks, John. So yeah, just as an overview, I will basically talk about AMTI Power's vision, AMTI Power PLC now, because we recently floated on the London Stock Exchange market. So we're now an AIM listed company. So I'll just talk about the vision, just the company and the history as well, historical links with lithium-ion battery industry in the UK. I will also just touch on how our strategy approach to meeting volume needs via the Tulsa pilot plant in Tulsa, as well as the UK Beacon and potentially an AMTI gigafactory. I will also touch on our cell types and the markets that we're targeting, as well as a typical cell development cycle. And I'll just touch on some chemistry roadmaps, not just our roadmap, but global roadmaps as well. Go to the next slide. Right, so in terms of our vision, can you see the next slide?
Yeah, that's coming through fine.
Yeah, okay. So in terms of our vision, it's simple, really. We just want to be a leader in innovative battery cell solutions. So we want to be able to provide for a niche market, and we want to have products or cells that are differentiated, that can be differentiated from those in the market, cells that you cannot readily access via the existing supply chain. So in terms of our company, we're a cell manufacturer, and we do have a strong heritage, leading back to what I would say called the innovation of lithium-ion batteries in the UK. We have about 60 employees. We have a pilot plant in Tulsa in the Highlands. And we also have a development facility in Oxford. That's mainly engineering based at the moment. And one of the key things we do as well is innovation and IP is quite important for us. So it's not just trying to scale up cells and manufacture cells, but during the early stages, being able to license IP where we can and add innovation into our cell development cycle so that we can continue to improve the cells as we progress from generation to generation. So as you can see from the next slide here, we are actually positioned at the heart of the battery supply chain. So our main focus is on supplying electrode materials, for instance. So our main focus is on cells, scaling cells and making cells. But at the same time, we do supply electrode materials. So we work with a lot with companies that do not have their own scale-up facility. We work with them to scale up their technologies, but we also have close links with other elements of the value or supply chain, if you like. So we work quite closely with raw material suppliers, as well as the finished products for batteries. We don't make modules or packs, for instance, but we have a partner that works with us to assemble ourselves into packs. We also work closely with some automotive OEMs, and we are involved as well in what I call second life as well as recycling. You can call it upcycling and recycling. So in terms of our history, like I said, we have some very strong links, if you like, with the lithium-ion battery industry in the UK. I think it all started in late 1980s, when John Goodenough, of course, being funded by AEA Technology at Oxford, came up with the lithium carbide oxide. And in 1998, there was a joint venture formed called AGM. So essentially, it's a joint venture between AEA Technology, and they were the technology provider, GS Yuasa, as well as Mitsubishi Materials. So GS Yuasa were the cell manufacturers involved in that venture. ABSL basically bought out that joint venture in 2007. And in terms of the key dates in this timeline here, AMTI Power itself was founded in 2013. And we actually started scaling up and making cells on a fairly small scale in 2015 at our facility in Torso. And we launched our product range, the Ultra range, in 2018 and 2019. So again, this is our Torso facility here. It's a pilot plant. So at the Torso facility, I would say we have a capability of maybe 10 megawatt hours per year. I rather define it in terms of megawatt hours per number rather than number of cells, because the number of cells depends on the size. So it's capability of about 10 megawatt hours per year. And we are chemistry as well as format agnostic. So we look into a range of chemistries. It could be a primary as well as rechargeable lithium-ion chemistries. And we also are looking into cylindrical and power cell formats. Historically, the facility was actually used to make these cells, cylindrical cells for the military. So the question is, we have a pilot facility in Torso. Like I said, we tend to focus on differentiated products for a relatively niche market. So those are relatively small volumes. But we also have aspirations to make cells in much larger volumes as well. And that's where we scale up to. We're looking into a Torso Plus facility to increase our current capacity. Then moving up from there in terms of scale, of course, is the UK BIC. I think they have the capability to make, or the capacity to make, I think it's hundreds of megawatt hours. Then up on from there, then for much larger volumes again, we're looking at an AMTI gigafactory. So you can see the timelines as well associated with those various activities. So in terms of a gigafactory, we're looking at 2023 to 2024. So again, these are the benefits of a gigafactory, apart from employing people, skilled people. There will be further support of various jobs across the supply chain, pack manufacturers, automotive OEMs, and end-of-life management companies. That again relates to the upcycling and recycling that I talked about previously. So now I just move very, very quickly onto our cell types and the target markets as well. So we have 4 key cell types, and we call it the ultra range. So we have the ultra high power cell. It's a powered cell, and that's basically targeting applications like track, performance cars, and aerospace as well. So vertical takeoff and landing, you need power for that. Then the ultra energy cell, for instance, I mean that's targeting mainly your electric pure electric vehicles rather than hybrids, as well as renewable energy and domestic energy storage as well. So with the renewable energy, we're talking about onshore and offshore applications. We also have a primary cell. It's a CFX-based chemistry. It's a high-temperature CFX-based chemistry. So that's mainly for downhole applications. That's called the auto prime. Then there's the auto safe chemistry, which is based on sodium ion. Again, we're targeting markets in the energy storage sector. So if you have a look, this is the ultra high power cell. For instance, this cell is capable of up to 600 C pulses. There's no such cell on the market. It's also capable of very, very fast charge as well. Charge rates over 35 C. There's always a trade-off, because when you increase the power, to increase the power, you have to increase the electrode. You have to decrease the electrode loadings. You have to make the electrodes thinner. So of course that will have an effect on the energy density. But the key performance matrix with this cell, the USP, is the power capability. Then we also have the ultra energy, like I talked about, I mentioned earlier on. So this is a 21700 format, for instance, and it uses a silicon oxide graphite-based anode chemistry and NCA cathode chemistry. Again, we are targeting just over 235 watt-hours per kilogram here. You can see this is a relatively low rate cell, so it's 1C as compared to the very, very fast discharge for the previous cell that I mentioned. An ultra safe cell as well. This is based on a sodium ion chemistry. You can see from the nominal voltage, again, this is relatively low rate. So what you can see is that I've shown you cells with different sizes and different formats. So we have that flexibility that a lot of large cell manufacturers don't have. Again, this is just showing you the specification for the high temperature lithium CFX cell. You can see the key differentiator with this cell is a low of self-discharge. It's reliable, it's got low self-discharge, and it's quite safe. I mean, currently, thionyl chloride cells are being used for this application, but they've been found to be very, very unreliable, unsafe as well. Explosions have been mentioned that can tend to happen with these cells, and with thionyl chloride's chemistry as well. What you can find is that the lithium passivates if you leave it lying down there for a bit, and what tends to happen is that you basically have to short the cell to get it going again, to get rid of that passivation film. So it's a low self-discharge that is one of the key benefits of this, and the reliability and safety. So a typical cell development cycle, I mean, I've used innovate, commercialize, and supply, and that's what we tend to use. Those are the terms we tend to use in-house. It's much more, our customers understand that a lot better. But typically we'll be talking about TRL and MRL levels as well. So a typical cell development cycle starting from the innovation phase, or what I call the proof of concept phase, all the way to production, can take as long as 24 to 36 months. A lot of people are not realistic as to how long it takes to get cells to market. You know, I've worked with the like with Sony, LG, and companies like that. And even for companies like that are quite well established in the business, it does take a while to get cells to the market. So we typically go, in our case, it's a 5-stage process, beginning with the proof of concept all the way to production. So you have these stages in between, the fully functioning prototypes. That's where you have your A model, B model, and C model. Then there's a milestone where you complete and finalize the design, which is the decaf. Then you have your engineering builds. At that point, you almost be optimizing for engineering and for manufacture. Then you have design validated and complete, then production. The innovation phase is very, very important for us as well. It's during this phase that we screen and down select parameters. For electrode parameters, for instance, the cell parameters to achieve a certain cell specification. It's at that point as well that you specify the cell. So it's not just material electrode parameters you're specifying, you're actually specifying the materials, active materials, passive materials as well in the cell. So you do some what I call development work or lab scale work or characterization work. You do some tests in Swagelok cells, for instance, or whatever test vehicle. You could use coin cells, you could use single layer or bilayer cells. Then following that, we look into the prototyping, and during this stage, this cell development cycle, for instance, is stage gated. There's a design review at each stage of this until we get to a point where you see where we will get to in Tulsa is up to TRL 7 because of the volume limitations. Then following that, we move things over to the UK BIC, and even following that, the production where we need quite larger volumes. Of course, it's the Gigafactory. This is a confidential slide. So this is a typical development cycle for the ultra high power cell, for instance. We would tend to engineer and design for different performance parameters at each stage of the cell development cycle. For instance, we might be optimizing for power, trying to reduce the resistance. We also might be optimizing for cycle life. So what you can find is that when you move, as you progress the cycle, you might have a slight decrease in a particular performance parameter. For instance, you can see this decreasing from 155 to 144 watt-hours per kilogram. That's because there are certain design elements that you have to change if you want to optimize certain parameters. I can't go into any details about this, but we've increased the power significantly, or the specific power capability of that cell, even though we've decreased the gravimetric energy density slightly. Then here again, this is just giving you an overview of the roadmaps. At AMTI, I think what we're doing is very heavily aligned with, I think, what's accepted globally. So in order to increase the energy density of the cells, we are adopting the approach of, for instance, increasing the specific capacity of the anode, and to do that is by increasing the amount of silicon or silicon oxide is what we use in the anode. Then with the cathode, of course, is increasing the amount of nickel, because that's the main redox active component in there. But of course, when you increase these things, there also comes the challenges. So you have to look into ways of mitigating, addressing some of those challenges by optimizing not just the way the materials are made. You could use electrolyte additives as well. So that's the approach. Then lithium metal, there's a lot of interest in lithium metal as an anode. We know what benefits that will give you, but there are still some challenges relating to cycling, dendritic growth, and safety So we're following that quite closely, and we're involved, and we're working with research establishments, universities, into finding ways of mitigating this. Then there's solid state, of course, the holy grail, but we know that there's still quite a lot of challenges. So some of those challenges are electrochemistry related, some of them are engineering related, some of them are simply design related as well. So it's not a straightforward solution, as some companies may make it appear to seem. So you can see some of the other roadmaps as well from CATL, for instance. That's one of the largest cell manufacturers in the world. So they're adopting a similar approach. I think their timescales for solid state batteries that come to market is 2025, which I think is very, very optimistic indeed. I put 2025 there, but I think it's 2030 and beyond that is looking more likely. And with that, I think that ends my presentation. Thank you very much for listening.
Thank you very much, Emmanuel. Very impressive. There's a bit of an echo, which is disturbing me. I'm not sure where it comes from. So, yeah, thank you both. That's really helpful and interesting. I should probably go straight across to Ian, who's going to host the questions. So please upload questions as you go forward.
Yes, thanks, John. Sorry, still get a bit of an echo from you, John. Okay, thanks very much, both of you, for your presentations. I've had a few questions come in, and I'm going to start with a bit of a general question to both of you. I'll start with John, and then I'll pass on to Emmanuel with the same question, which is, although you're working perhaps in slightly different sectors, you're obviously both working in fields which are intending to grow over the next decade or so. The move towards a hydrogen economy, the move towards a demand for electric vehicles, there's going to be increasing demands for precious metal-based chemistries. And do you see any issues with availability of raw material and, I suppose, associated with that, issues around, for example, geopolitics, the ethics of sourcing raw materials, and that kind of thing? John, can I start with you and see what your thoughts are on availability of raw materials?
Yeah, absolutely. It's very close to what we are looking at. Yeah, as I sort of alluded to in the presentation, we have a very close relationship with the mines and companies. Our own company and other companies are providing that raw material. So we know there's a finite resource. That's why we have a strategy of trying to maximise how much we can use and where we can use it to. Again, we have discussions around, look at the price of iridium, where it's went to. Should we then start thinking about is platinum, an alternative in there as a stopgap? Again, this is sort of further down the chain, not exactly where we are, but I would see other companies also taking an approach of could we make, for example, a fuel cell or an electrolyzer that's not as a robust piece of equipment, but something that could actually function with lesser material in there. I don't know if that's a strategy that would take, but there will come a point where the precious metal is going to be a key factor. So we've also discussed around the whole process of taking old MEAs, the electrode assemblies, which are coated, and can we actually recycle that? So again, there's that whole environmental question in there as well. If we could actually take these and reuse, and can we separate the platinum from the iridium? Can we reuse the electrode the electrolyte itself. So we have started that as a project just now, and we are actually working quite closely with other universities and manufacturers around this whole issue. But we see it as a 10-year. Response to get that back.
Sorry, just a momentary delay with unmuting there. No, that's really interesting. Thank you. I've got a couple of specific questions for you in a moment, which we'll come back to. But Emmanuel, your thoughts on raw materials and to the extent to which that might impact your trajectory as a company over the next few years.
Yeah, that's a very, very good question, isn't it? Because that's why we tend to. I mean, the bill of materials is quite crucial. Consolidating the supply chain is very, very important. That's why, I mean, for instance, like the nickel-rich materials, I mean, nickel is going to be in very, very high demand. People are trying to phase out cobalt or reduce the amount of cobalt, and that's why what we tend to do is we tend to extend who we work with. For instance, we're currently working with a material supplier, the supplier of the raw materials in Australia, for instance. So we're beginning to look into diversifying to avoid coming across this issue of limitations of what you can do because of the materials that you use. But like you say, it potentially could be a problem and could be limiting. But we are looking far beyond just the UK to address some of these challenges or potential challenges.
Great, thank you. And while you're on, Emmanuel, a couple of specific questions have come in for you, which are so specific I don't even understand them, but I'm sure you will. Do you plan to produce your sodium-ion chemistry in the 21700 format? And similar to that, do you have plans to incorporate Tesla's tabless electrode design into your cylindrical cells?
Right, they are very good questions. Cylindrical, I think in the near future, at least in the next year or two, I think the focus is on pouch cells for sodium-ion. The simple reason for that being that compared to the other lithium-ion battery chemistries, for instance, it's relatively less developed. So we want to focus on developing it in a relatively straightforward format. I think the requirement for that is a pouch cell just now. There's absolutely nothing preventing us from developing it in a 21700 format. In fact, I've actually put together a target cell specification for sodium-ion in a cylindrical cell format, but it's just not an approach that we are following right now. It could be in the next 2 years, potentially, once we've been able to get our pouch cell across the line. And the second question, could you remind me of the second question again? Sorry.
Do you have plans to incorporate? Oh, sorry, that you put the cylindrical cells, Teslas, and the 21700 format.
Yeah. The other one was the tabless. Yes, we are looking into that. But you have to look into freedom to operate considerations and infringing on IP and stuff like that. But we can see that will be of immense benefit in terms of reducing the internal resistance of the cell. We're looking at similar approaches, reducing the number of tabs and minimizing the internal resistance, especially for cylindrical cells, for the ultra high power, because I didn't present it today, but we are also looking at an ultra high power variant as well in the cylindrical cell format. And for that, reducing the resistance is going to be quite crucial because intrinsically, inherently, pouch cells lend themselves to lower resistance than cylindrical cells. So through engineering and design optimization, we're going to have to find ways of reducing that internal resistance.
Okay, thank you. I'll just come back to John now. There were a couple of that are coming for you, if I could, John. Somebody's asked on the reuse issue, because you did touch on reuse, I think. Have you considered using recycled catalytic converters as your source of platinum?
Not directly here. I mean, I know other companies will be doing that, and that will be a larger scale thing. So, if again, what I said right at the beginning, if you're refining that material, you have to be very careful how that refined material then becomes one of our starting materials, because there is a quality issue in there. So as I said, if we have virgin ore, then that virgin ore that would have, let's say for example, low iron, low chromium, you know, a whole suite of metals in there, which would be way down in the parts per billion range, and things like the platinum could be up as high as 1,000 parts per million. But then if it's a recycled material, and then even if we make it into a salt, a metal salt, that tends to follow through, even though you have a recycling and refining methods. Those trace impurities tend to trap themselves and come through. So virgin refined material is perfect for us. But I know that we can still work with refined material, but to really go back and say, you know, catalytic materials from exhaust, yeah, it's there, it's available, and I'm sure in the future, you know, it could be used as a starting material for us. But I think there's other uses where that quality of material is probably better utilised elsewhere.
And a question came in earlier that is probably quite interesting for context here. Somebody asked roughly what proportion of capital expenditure these materials represent in electrolyzers.
It's not as much as you think. It is still significant. I can't remember off the top of my head, but it's not like, I think it's down about 10% from memory, something like that. And obviously this is something that's ongoing. And fluctuates, as you can see. I mean, when the iridium's at $2,000 per troy ounce and then 6, then obviously that has a multiplier of 3 at that stage. So that's a moving target, but it's not as high as you would think. I mean, there are other components in there, and I'm talking specifically on fuel cell or electrolyzer PEM technology here. That things like bipolar plates, your titanium that goes in there. These are all expensive parts as well, and it's just a follow through in the whole thing. But if you can actually reduce that cost, then fantastic. I think the biggest improvement you're going to see going forward is as you scale up into gigawatt electrolyzer scale, is actually the use of the iridium. It's actually spreading it out, and because, as I said, 8,000 kilograms per year, you know, it's not a lot, but there is certainly enough there from our calculations. And if we can do a 10% loading as opposed to 100% loading on your MEA, then I think that's where you start to really see the benefits of cost reduction.
Yeah, and I can see this is where the electrical efficiencies come in. I'm just going to go to Emmanuel for one final question before we wrap up, because Emmanuel, somebody asked earlier, how does the performance of your ultra range of cells compare to what's currently available in the market?
I would say it's comparable. It's competitive. For the ultra high power cell, for instance, there's nothing that would give those kind of performance levels on the market. For the ultra energy cell, I would say the first generation, which I tend to call a Me Too cell, if you like, that will be comparable to cells on the market. So I would say comparable performance. Things like the ultra prime cell, for instance, there's no such thing on the market. High temperature primary cells, but our performance will be significantly better than the thionyl chloride.
Okay, that's really good. Thank you so much. We're just coming up to time now. John, I'm going to pass back to you to close off and to give us a quick commercial break for the Next Industry Club. Thank you.
Yeah, it's been shown for me. So thank you very much to both of you, and I think we can still keep the questions live, and you can respond. There's a number of questions there that haven't been we haven't had time to air. If we ever go back to normality, this might be the time to retire to a few glasses of beer or coffee, and so I think we'll have to make do with filling in questions and answers. So just say in a month's time we continue the series. These have been fantastic, and it's really nice to get this engagement, and we're building up a community which, as I say, hopefully we'll be able to get together and follow up with. So the next two speakers are Royston Jones from Altair and Jamie Hillis from Sunamp, and that's Tuesday the 27th of April from 1 to 2 again. So thank you very much, and have a good afternoon, and happy Easter to all of those who are not based in St Andrews University and take Easter as a holiday.
Thank you very much.
Cheers.
Thanks.
Thank you.
Okay, thanks a lot.